Good morning, everyone. Welcome to today's presentation. I'm excited to share with you some fascinating insights about the universe. This is our first slide, and it's the cover slide, so I'll keep it simple. As you can see, the title is Universe, and it's for Class 10. Today, we'll be exploring what the universe is, its vastness, and some interesting facts about it. So, let's get started and dive into the amazing world beyond our planet. After the Big Bang, gravity played a crucial role in shaping the universe. It pulled together matter that was initially spread out evenly, leading to the formation of large structures like galaxies, stars, and planets. This process is fundamental to understanding how our universe came to be in its current form. Moving on to the stability of planetary systems, gravity is the force that keeps planets in orbit around their stars, like Earth around the Sun. It also governs the orbits of moons around planets and satellites around Earth. Without gravity, these orbits wouldn't be stable at all. Planets and moons would drift away into space. So, in essence, gravity is the key force that holds everything together in our universe. Without it, there would be no stable structures or systems, and the universe as we know it wouldn't exist. Recognizing this helps us appreciate just how vital gravitational force is to the very existence of the universe. The Big Bang is our leading scientific explanation for how the universe started and has evolved over time. It suggests that about 13.8 billion years ago, the universe began as an extremely hot, dense, and tiny point known as a singularity. From this tiny point, the universe has been expanding ever since. Think of it this way. The universe is believed to have originated from a massive explosion, similar to a superenergetic burst from a single atom. Before this explosion, the four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were actually unified into one single force. In that very first moment, the universe was in an incredibly compressed state. Imagine all that energy packed into something about the size of a small atom. The pressure and forces at play were so intense that they triggered this colossal explosion, giving birth to everything we observe today. This concept helps us understand not just the origins of the universe, but also how it has been evolving and expanding over billions of years, connecting deeply to our broader exploration of cosmic evolution. Now, let's try a simple experiment. I place two dots on a balloon, and then I start to inflate it. As the balloon gets bigger, I observe what happens to the distance between those two dots. What I notice is that as the size of the balloon increases, the space between the dots also stretches out. This is a really useful analogy for understanding the expanding universe. Just like the balloon, our universe is expanding, causing galaxies and other cosmic structures to move away from each other. So, in essence, the expanding balloon is a helpful way to visualize how space itself is stretching over time. This comparison highlights a key concept in cosmology. The universe's expansion affects everything within it, just like the dots on the balloon. All right, let's take a look at Hubble's law. This is a fundamental concept in understanding how our universe is expanding. Essentially, Hubble's law states that the farther away a galaxy is, the faster it's moving away from us. This relationship is expressed as a direct proportionality between a galaxy's distance and its velocity of recession. What makes this so exciting is that it provides strong evidence for the Big Bang theory, the idea that the universe has been expanding since its very beginning. When we observe distant galaxies, we see them moving away faster, which suggests that space itself is stretching. This law also helps us estimate how old the universe is, based on the rate of expansion. The constant of proportionality, called the Hubble constant, tells us how quickly the universe is expanding at present. So, in the context of our overall theme, Hubble's law not only helps us understand the universe's current state, but also connects to its history and future evolution. It's a key piece of the puzzle in cosmology, giving us a way to measure and comprehend the vast, dynamic cosmos we live in. Let's take a closer look at the value of our constant, which is 73 kilometers per second per megaparsec. Now, what does this actually mean in practical terms? Well, it tells us that if two galaxies are separated by a distance of 1 megaparsec, their relative velocity, that is, how fast they are moving away from each other, is about 73 kilometers per second. This measurement is fundamental because it helps us understand the rate at which the universe is expanding. Now, moving on to Hubble himself, what was his key discovery? Hubble found that the universe is not static, it's expanding. This was a groundbreaking realization because, prior to his work, many believed the universe was unchanging. His discovery provided strong support for the Big Bang theory, suggesting that the universe had a beginning and has been expanding ever since. So, in essence, Hubble's observations link directly to the idea of cosmic expansion, giving us a way to measure and understand the universe's growth over time. This constant, often called the Hubble constant, is central to our understanding of how fast the universe is expanding today. Now, let's talk about the future of the universe and some of the key concepts related to its ultimate fate. One important idea is the average density of the universe, which we call the critical density. This is the density needed to stop the universe from expanding forever. If the universe's density is exactly at this critical level, it can tell us a lot about what might happen next. Depending on whether the density is above or below this critical point, the universe can have different geometries. An open universe, for example, would continue to expand forever and has a density less than the critical density. A flat universe, on the other hand, has exactly the critical density, and its expansion slows down but never quite stops. Then there's the closed universe, which has a density greater than the critical density. And in this case, gravity can eventually cause the universe to stop expanding and possibly contract. Understanding these possibilities helps us connect the dots between the current observations and what the future holds. It's fascinating because the critical density acts as a kind of cosmic threshold, shaping the ultimate destiny of everything we see around us. Let's start with the open universe. When the average density of the universe is less than the critical density, gravity isn't strong enough to hold back its expansion. As a result, the universe keeps expanding indefinitely and will continue to do so in the future. We call this an open universe. Moving on to the flat universe. Imagine a scenario where the gravity and the velocity of celestial bodies balance out perfectly, so that they essentially stay in the same position over time. This creates a stable universe. In fact, if the density of the universe equals the critical density, we observe this flat universe. Finally, let's discuss the close universe. Here, the gravitational force remains non-zero, but the velocity of celestial bodies drops to zero. Without enough speed to escape gravity, these bodies start to move closer together, leading to a collapse. This results in what we call the Big Crunch, a scenario where the universe's mass and energy collapse into a single point. This happens when the density exceeds the critical density. Connecting these ideas, the key takeaway is how the balance between gravity and expansion determines the ultimate fate of our universe. Thank you for your time and attention today. I truly appreciate your engagement throughout this presentation. I hope the insights shared have been helpful and have provided a clear understanding of the key concepts we've discussed. Remember, the ideas and strategies we covered are meant to support your ongoing success. If you have any questions or want to explore these topics further, please don't hesitate to reach out. Once again, thank you for being here, and I look forward to connecting with you again soon.